Hey guys, what is going on? Today we're looking at Algebra 3's 11.6 fundamental counting principles, permutations and combinations. I can't type or spell apparently, but I can, luckily for you, do math. And so here we are. Hey, I spelled it correctly here. Solving real world examples using the fundamental counting principle, permutations, and combinations. So let us get into it. This is strictly review from Algebra 2, but I'm refreshing your memory because I'm sure you've all forgotten everything, just like you always do. Students always forget everything, and so here we are, teaching the same material year after year after year. The fundamental counting principle is the number of ways in which a series of successive things can be done, and you multiply the number of ways each thing can occur. So, example 1 says that next semester you plan on taking 3 courses: math, English, and humanities. There are 8 sections of math, 5 of English, and 4 of humanities. Assuming there are not scheduling conflicts, which means that you can choose any of the math sections, any of the English sections, and any of the humanities sections, and none of them conflict with each other, how many different 3-course schedules are possible? You might be thinking, what do you mean 8 sections of math? Well, in college, if you're not concurrently enrolled, you don't know this probably, but there are tons of time slots. It's mostly time slots and also professors, I guess. That's another big factor for every class, most classes. So when you take, college algebra at a community college, there could be 3 or 4 teachers who teach it. And there could be like Monday, Wednesday, Friday classes, Tuesday, Thursday classes, Monday, Wednesday only classes, Tuesday only classes, Thursday night classes, whatever. There could be 8 different sections of that college algebra by different teachers. That seems like a pretty low number to me, actually. So that's your explanation of that. 5 Englishes and 4 humanities. Now, the question is, assuming they're not scheduling conflicts, how many different schedules are possible? So, to run this by you, one schedule might be section 1 of the math, section 1 of the English, and section 1 of the humanities. Schedule number 2 might be section 1 of math, section 1 of English, and section 2 of humanities. Right? So there's obviously a bunch. So the idea with the fundamental counting principle is that you take the total number of each and you multiply them together. You've got your math, your English, and your humanities. And there's 8 math, 5 English, and 4 humanities, and you just multiply them together, and that's that. And so you have 8 times 5 times 4, which 3,200 or something. 8 times 5 times 4, 160. I was way off. 8 times, yeah. All right. 20, yeah, that makes sense. 20 times 8 times 8, 16 plus a 0. All right. So, 160 different schedules. I know that the ACT has questions just like this. I see it all the time in ACT prep. Example 2. You are taking an 8-person multiple choice test. There are 4 possible choices for each problem and only 1 correct choice. Assuming that all possible choices are equally likely, how many different ways can you answer the questions on the test? Which means that how many different ways is like how many different tests could be taken and submitted, right? Like you and your neighbor have different tests, right? How many different tests are possible? That's what the question here is asking. If you just think on the surface, on the last question, I multiplied the numbers together and I got the answer. And if you think to do that on this one, you're going to be way, way off. Way off. If you just multiply 8 times 4, you'd get 32. So you'd have to ask yourself, think, step away from the math and think about just logically. If there are 8 questions on a test, and there are 4 questions, or there are 4 choices on each question, how could there possibly be as few as 32 different tests in total? That's saying that if there are 32 kids in your class and you all answer differently, one of you has scored a 100% and one of you has scored a 0%, and the rest of you have scored everywhere in between. That is totally crazy. There's no way. Let me give you an idea. There are 8 questions. 1, 2, 3, 4, 5, 6, 7, 8, right? Person number 1, I'm going to start with an exhaustive list here to give you an idea of just how wrong this is. Person number 1 could answer A, and turn the test in. That would be one test. Person number 2 could do A, B. Person number 3, A, C. A, D. A, B, A. Then A, B, B. So you see that this is a crazy number. So it is not 8 times 4. But what you have to think is for each slot, which is each question, or each category in the previous example, how many choices exist? And it would be 4 choices for each question. And what you end up doing is taking 4 times itself 8 times. And that is a much, much, much larger number. It is 65,536 different tests. That is the answer. Example number 3. Your 13-player baseball team needs a batting order containing 9 players. For batting orders, the order of players matters. That will come into play later on. How many different batting orders are possible? So the idea here for the fundamental counting principle will be to think as slots. Slot number 1 all the way down to the 13-person team. Or actually, wait, for 9 players. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 13 people to choose from for the first slot. But now since one has been chosen, they can't bat again. So then there's only 12 choices, and then there's 11 choices, and then there's 10 choices. This is a really common way to do these questions, where you make, in my opinion, this is the easiest way to do this. You make slots for each choice, and then you put the total number of people that can apply for the slots in them as you go from left to right. So there could have been 13 people in this one, but then only 12, and then only 11, and then only 10, and then only 9, and so on. And if you do this, 13 times 12, you get such a massive number, times 11, times 10, times 9, times 8, times 7, times 6, times 5. You get, oh my god, 2, 5, 9, 4, 5, 9, 2, 0, 0. Oh my god, that's so many different batting orders. That many different batting orders. This calculation can also be done by taking a permutation, another review concept. A permutation is an ordered arrangement of objects where no object is used more than once. The order of the objects makes a difference. This is a key thing. The order of the objects makes a difference. For the example above, we have 13 objects taken 9 at a time. This is denoted as 13p9, read as the number of permutations of 13 things taken 9 at a time. This follows a specific formula, and this is the formula. You won't need to use it because you can use your calculator. If you have a TI-84, listen carefully. Press Math. Go over to the Probability tab. In the Probability tab, there is an NPR choice. That is what we'll be using. Now, if your calculator is old, your calculator will, when you press Enter on NPR, it'll say NPR. And to use it, if your calculator is old, you'll have to put the first number in first, then go into the calculator and put the NPR in, and then put the R in next. So this would be N and this would be R, and then you press equals. But if you have a newer calculator, it'll literally give you little boxes that you put the numbers in. So I want to point out the order being important. So order is important. Let me tell you how you can know that. You have to imagine 2 selections or scenarios where the same people or things were chosen, but in a different order. And you have to ask yourself, did the outcome change by changing the order that the same people were selected in? So let's say that my baseball players are labeled, by these numbers, right? This is the number on their jersey. And this is the order of the batting team. Number 13 went first, number 12 is second, number 11 is third, and so on. If I choose the same people, but put them in a different order, say I give 10 and then 11 and then 12 and then 13, and then the rest are the same, 9, 8, 7, 6, 5. These are different batting orders, right? But I chose the same people. That means this is absolutely a permutation. If you can choose the same people in a different order and get a different outcome, which in this case is a batting order, that is a permutation. This can be done by taking n is the total number, 13, and r is the number you're selecting out of that, which is 9, and this is 13p9. The math for that is n factorial over n minus r quantity factorial. So this would be 13 factorial over n 13 minus r quantity factorial. Do that, and you would have your number of different batting orders, which would be the same as this. All right. Example number 4. A class of 30 students needs to choose 3 officers, a president, a vice president, and a treasurer. In how many different ways can those offices be filled? So like how many different cabinets can be had? You have to ask yourself, if you're doing this with the fundamental counting principle, how many different ways can it be done? Do you think there are 3 slots? President, vice president, and treasurer. There are 30 choices for president. If you chose one, then now there are only 29 choices for VP and 28 for treasurer, giving you a grand total of 30 times, 30 times 29 times 28 is 2,4,360. And you have to ask yourself, how is this a permutation? Here's how, right? Say the students are numbered. Number 1, number 2, number 3, right? Every student has a number. If I chose number 1 to be the principal, or the president, number 2 to be the vice president, and number 3 to be the treasurer, and then I chose the same 3 people, it's very important it's the same people, but I put them in a different order. So I say number 3, then number 1, and then number 2 for the president, the vice president, and the treasurer. Does the outcome change for the cabinet or the individuals? The answer is absolutely. Person number 1 went from being the president to being the vice president. And person 3 went from being the treasurer to the president. Even though it's the same people, it is absolutely a different cabinet, which means that this is a permutation. And if it's a permutation, then n is going to be the total number, which is 30, and r is going to be the number we're selecting, which is 3. And so it is 30p3, which is 30 factorial over 30 minus 3 factorial, which is 30 factorial over 27 factorial, which is 30 times 29 times 28 times 27 factorial over 27 factorial. The 27 factorials cancel, and you get 30 times 29 times 28. Hey, that looks familiar. Like this. Not a coincidence. Now, take a drink here while you read this. I've been talking for a long time today. Combinations. Combinations are selecting an arrangement of objects where the order does not matter. Here is a nice example. Santa Claus, the generous guy he is offering you 3 free gifts of your choice out of 100 possible choices. How many ways can you select the 3 gifts? So how many different 3 gift combinations can you create? Now, here is why this is a combination and not a permutation. Let's say you select in your very meticulous selecting gift number 36, gift number 47, and gift number 72. If you selected those gifts in that order, it would not matter to you if you had selected them in this order or in this order. Number 47 first, number 72 second, and number 36 next. Why would that not matter? Well, because at the end of the day, you still got the 3 free gifts. You still got the same gifts. You're still taking them home. It doesn't matter. So in this case, the order of selection does not matter, making it a combination. If this is the case, that means that the number of possibilities will drastically reduce. And that is because in permutations, when we consider these two to be separate outcomes and we totaled them all together, you don't consider them separate outcomes, which means you're drastically cutting down the number of outcomes that are possible. There are far fewer combinations given the same total and number of selection than there are permutations. And that is because when you select the number, a permutation considers the mixing of these to be different outcomes, right? The mixing of these being different outcomes, whereas combinations don't consider them to be different outcomes. So this is the formula for combinations. N factorial over R factorial times N minus R factorial. This is exactly the same formula for N above R. So give me a second. I'm going to transition over here to the next slide. All right. A 3-person committee is needed to study ways of improving school attendance. How many different 3-people committees can be formed from 8 total people? Note, each committee position has the same responsibilities and job title. First of all, to know that this is a permutation or combination situation, you're looking for how many different arrangements can be made, right? The how many different committees can be formed, that's like a key phrase for combinations. How many different ways can this be done? Those are like phrases you're looking for to know you're doing permutations and combinations. And then you have to ask yourself, is this a permutation or is this a combination? The key idea behind this lesson is differentiating between permutations and combinations. And let me tell you, again, the best way to know this is to imagine 2 scenarios where the same people are chosen, but in a different order. And you have to ask yourself, is the outcome different if I chose the same people in a different order? So let's ask ourselves that question for this problem. If I chose person 1, person 2, and person 3 for my 3-person committee, and then, so that's one committee, and then I chose person 3, person 1, and then person 2, in that order, is the committee the same committee or a different committee? Are these the same? The answer is yes, they are the same committee because each person has the same responsibility and title, so they're all in the same committee. So yes, this is a combination because since these are considered the same, that means the order does not matter, which means this is a combination. And so this is going to be 8C3. That's going to be 8 factorial over 3 factorial times 8 minus 3 factorial. You put that on a calculator, that's going to be 8C3, which is 56. I want to point out, you don't use the fundamental counting principle for combinations, all right? Fundamental counting principle can only be used in situations where the order is significant. At least the way that we've been teaching it here. All right, that wraps us up. You guys work on your homework. Everything will be good. Ask questions if you need help, and I will see you on the next one.